This is a pre-recorded version of the discussion for Monday, March 17th. Because we have a guest speaker in class, I've gone ahead and recorded the notes that I would have presented to you all in class. This is where we left off on Friday with our discussion of different sizes of big O notation. What we've got here are the abilities to compare things of different sizes. Powers, the larger power dominates the smaller power. So notice D is bigger than C. N to the C is big O of N to the D, but not the other way around. All logarithms are compressible below big O of N, no matter what the base is, no matter what kind of logarithm we're doing, they're smaller than big O of N. Every exponential dominates every power as long as the base is bigger than 1. Because if the base isn't bigger than 1, then my exponential is not growing, it's actually shrinking. And larger bases dominate smaller bases. As an example, take a look at problem, where is it? Sorry, example 8, here on page 224. It lists several different big O's, and it asks us to put them in order. So I have 8 root n, log n quantity squared, 2n log n, n factorial, 1.1 to the n, and n squared. Well, let's think about smallest. What would be the smallest? Well, powers are smaller. Oh, wait, logarithms are smaller than powers. Logarithms smaller than any powers, even n to the 1/2, but n to the 1/2 is the smallest power here. So that's going to be my next number up. So log squared is smallest. 8 root n is next. Then n log n. Well, root n is smaller than n, and log n would be bigger than n, but only barely, but still smaller than n squared. And then exponential, and then factorial. And all of this works based on these 4 primary rules. But in a lot of cases, we don't just get one function, we get a bunch of them stuck together. For example, something like please note, I did not write a base on that logarithm. Now, being a mathematician, normally if I don't use a base, I think natural logarithm. If you're in the physical sciences, when you don't use a base, you think log base 10, common logarithms. If you're in computer science, and the way this textbook works, it writes log x to mean the log base 2 of x. It thinks in binary. That's okay. All log bases are equivalent because remember, we have the change of base formula, which really makes every logarithm, no matter what it is, a multiple of ln. That means they're all equivalent no matter what the base is. It's this plus that's the problem. I don't know how to deal with that plus. So I need a new theorem. The theorem says if F1 is big O of G1 and F2 is big O of G2, then their sum is big O, not of the sum, but of whichever one is bigger. So really, if you're adding, you don't ever get bigger than the biggest piece you're adding to. And that means I can go back to this function. I can say, oh, well, I've got a 3x cubed and I've got a logarithm. Which of those is bigger? Well, based on that giant list that I'm about to take off the top of the page here, I know that the logarithm is smaller than big O of n. Well, I'll use x. And 3x cubed is big O of x cubed. As a matter of fact, it's exactly equal to a multiple of x cubed. And that means this is the larger of the two. So my function, that is the sum, is in big O of x cubed. In other words, adding these pieces wasn't big enough to increase the complexity. By the way, this works when I'm dividing and multiplying and adding and all the rest of that, but multiplying. Oh, by the way, if both of these are equal, then the sum is equal. That's written as the corollary at the bottom of page 225. If I'm multiplying, F1 is in big O of G1, and F2 is in big O of G2, then the product F1 times F2 belongs to big O of G1 times G2. So when we're multiplying, that increases my big O, or decreases it, depending on how I multiply. Let's consider this function. There we are. F of x is x to the fourth plus 5 log x over x to the fourth plus 1. Now, those of you that took an algebra class may remember something about horizontal asymptotes. Those of you in calculus may or may not have already seen L'Hopital's rule. These are equivalent ideas. Let's write this as x to the fourth plus 5 log x times 1 over x to the fourth plus 1. And let's consider each of these pieces separately. X to the fourth plus 5 log x, just as our previous one. I hope it is clear when I say that is big O of x to the fourth, because the 5 log x is too small, like it was up here, to contribute anything. What about the 1 over x to the fourth plus 1? Well, x to the fourth plus 1 is big O of x to the fourth, which means 1 over that will also be 1 over x to the fourth. Or if you'd rather, you could write that as x to the negative fourth. So let's put those together. These are being multiplied. So that means that my function f of x is big O of x to the fourth times 1 over x to the fourth. Sorry, is in, not equals. Remember, that's an element of a class. But that means that f is big O of 1. All right, wait a minute. Wait a second. What's it mean to be big O of 1? Oh, well, that means as you go off to infinity, you're never going to get bigger than some constant. This tells me that this graph should have a horizontal asymptote. Let's actually graph it and take a look. Y equals, oh, got a bunch of other crap in here from the other day. So let's write in our function, parentheses, x to the fourth plus 5. Now, if I want to use log base 2, I can go to the math button, and way down here at the bottom, there is a log base 2 of x over parentheses x to the fourth plus 1. So there's my function. Now we'll graph this. But since I think this is going to have a horizontal asymptote, I'm going to graph this on a much smaller y window. When I see that, what's going on? Oh, there's my function. And as x goes off to infinity, that seems to be getting closer and closer to y equals 1. As a matter of fact, if we look at a larger x range, we can see it much more clearly that that's got to flatten out, isn't it? There we go. Now, finding witnesses would be a lot more difficult in this case. I could fairly easily say, hey, look, this function's always smaller than or equal to 2. So there's my witness. K equals 1, C equals 2. Normally at this point I would ask questions, but I'm recording this, so I can't give you the time to ask me questions, which means you should come ask me questions if you have them during my office hours, or you should email them to me. Meanwhile, big O is an upper bound. Which means I can create a lower bound. Here's a new definition. All I'm going to do is change the order of the inequalities. F of x is in capital omega of g of x if there exists two numbers, c and k, both positive, so that absolute value of f of x is bigger than or equal to c absolute g of x whenever x is bigger than k. So again, we have a witness, and this says that we are bounded underneath by a particular function. An important note, if f is in big omega of g, then g is big O of f. And vice versa. Well, I already showed you that x squared plus 1,000 was big O of x squared. That means that x squared is in omega of x squared plus 1,000. So we can bound above, we can bound below. Now, this is beneficial because we might want to do both at the same time. If f is in big O of, f is in big O of g and f is in big omega of g, then f and g are of the same order. And we usually write f is in theta of g. But that's the same as saying that C1 f of x, sorry, no, C1 g of x, because I wrote f and g. C1 g of x less than or equal to f of x less than or equal to C2 g of x when x is bigger than k. So instead of finding one witness, we find two witnesses. Almost always, when we are looking for the same order comparisons, we're trying to find the simplest function of the type x to some power or of the type exponential. We're looking for the smallest possible thing. So we're looking for x to the k, or we're looking for b to the x, or we're looking for x to the k log x. or something like that. We're looking for simple things. Advantage. All polynomials are big O, therefore big theta of their highest power. Every polynomial is of the order of its highest power. Always, always, always. Now, unfortunately, in computer science, we don't often look at functions. We look at algorithms. So what I really want to do is I want to take this idea, I want to apply it to algorithms. At this point in time, there are literally a dozen examples in the text that we should work through, but they're all printed out in full. I want you to read them. So the real question is, how do I apply this to algorithms? So as today's guest speaker will be talking about an algorithm we introduced on Friday, you'll have seen an implementation of an algorithm that you find familiar and thus know something about. So now what I want to do is I want to think about big O as a measure of efficiency. And that becomes a very important question in and of itself. What sort of efficiency are we measuring? So let's talk about efficiency. We can actually measure two different things. Given an input set. Remember, when we were doing our search algorithms, when we were doing our sortings, whatever we were doing, we looked at the size of the number of things we went in to figure out what we were going to do. So let's say we have an input set of size n. We can ask two different questions. How many steps? And the reason we count the number of steps is because computers keep getting faster. So counting the actual time isn't as important as knowing the number of steps. But this is really time. And the other question we can ask is how much memory do we need to implement the algorithm? And since that's actual physical hardware, we think of that as the space it takes. How many slots of memory, how many bits, how many bytes, how many meg of memory does this algorithm take to implement? And we have time complexity and space complexity. And the general coverage for both of these is called computational complexity. Almost all algorithms today are more concerned with time complexity than space complexity. Used to be the other way around. Remember, If you saw the movie Apollo 13, remember they kept trying to reprogram the computers on the uh, lunar modules because they were finite number of vacuum tube memory pieces. The total computing power of the Apollo lander was less than this. Those of you with a smartphone, we went to the moon on less computing power than your smartphone. But now space is dirt cheap. Your computer has a hard drive measured in terabytes. You can fit gigs on your thumbnail. It is quite possible, and I will bring it to class. I don't have it here at home with me, it's at the office. I have one of the very first megabyte memory chips ever issued by IBM. They've put them under glass and handed them out as souvenirs. But a megabyte would fit on my pinky, on the fingernail on my pinky. The original 5 meg hard drive needed to be loaded into a plane on a crane. Space used to be very, very hard to come by. Now space is dirt cheap, so everybody's concerned with time. As very large scale integration density increases, as we get faster and faster chips, then it becomes much more important to figure out how long it's going to take. So let me start with a fairly simple example. We'll search a list. Now we did this. We did this before break. So let's think about finding the largest number in a set of integers. And what we're going to do is we're going to measure a couple of things. We're going to measure comparisons. So the algorithm itself is back in the textbook on page 202. Let me turn to it, and then we will look at it together. On page 203, procedure, max, here's my set of integers. And we start by taking the first one and saying that's our biggest. And then we wrote the loop for I equals 2 to n if max is less than AI, then AI goes in to max. Otherwise, do nothing. And then when we're done, return max. So that's the algorithm as written on page 203. So let's figure out how many steps this takes. I have to do a bunch of comparisons, right? I have to compare I to n to run the loop. I go until I hit I equals n. So I have to keep track of what I is and compare it to n every step. I won't drop out until I hit n plus 1. So hidden in here, because we're doing a loop, is the counter increment. That's a bookkeeping thing. We're not going to count that one. We're only going to count the comparison. How many times will we do this? Well, I got to go from 2 to n. That's n minus 2 plus 1, n minus 1 comparisons. Then I have to compare within the loop each time. I have to compare max and AI. So for every time I run through the loop, I have to do this comparison. Well, that's another n minus 1 comparisons. Well, wait a minute. That's a total of 2 times n minus 1 comparisons, right? Oh, wait. I also am going to check this one extra time, right? Because I'm going to go one. I'm not going to really jump out of the loop until I hit n plus 1. Comparison to exit the loop. So that's n minus 1 plus n minus 1 plus 1, or 2n minus 1 total. And that means that if I think of this as depending on the size of the number of steps, I would say that this algorithm is big O of n. Why is it big O of n? Ah, it's big O of n because this is a polynomial. And the highest power of that polynomial is n to the first. Perfect. As a matter of fact, this is actually theta of n. That's the size of the complexity here. Again, more often than not, computer science people will speak of these two interchangeably as big O versus big theta. I'm perfectly fine just calling things big O, but we are technically calling things big O incorrectly. We're really using big theta. Again, at this point, normally I'd say, hey, any questions? So I want you to think about this because this is not immediately, intuitively always obvious. So I say, oh, here's the second number in the list because I already have the first number in the box that says maximum. So I move to the second step, compare. I move to the next step. Am I finished with the loop? No, because I'm still on 3 and that's less than n. So I'm going to do 2 comparisons for every step I take here. One to compare here and one to compare here. Okay, let's try another example. Remember our linear search algorithm? We had a bunch of numbers and we wanted to find a particular one in here. If I was looking for a particular number and I wanted to know, hey, where is it? Well, I could just say, what's the worst thing that could happen? The worst thing that could happen would be that the thing I'm looking for is where? It's there. Since the linear search requires me to go through one at a time. Oh, okay. Well, again, let's go back and look at the actual algorithm that shows me the linear search. And again, we wrote this before break. The linear search is on page 204. Procedure, linear search. It gives me the list A1 through AN, and it gives me the thing I'm looking for. Now, again, I'm doing a search on integers. You could be doing a search on any data type. Start with a counter. While I less than n and x not equal to ai, add 1 to the counter. If either of these conditions fail, then I know where I am. If I less than or equal to n, then location is I, else location is 0. It's not here. Print location. So, how many comparisons am I doing? Okay, here in this row, I'm doing 2 comparisons. I'm comparing I to n, and I'm comparing x to ai. This operation happens in the loop. If you want to count that, that's fine. So each twist of the loop does 3 operations, 2 comparisons and an addition. And I'm going to do that n times. Because once I equals n, we stop. We go one more time. I got to do n plus 1, right? So let me check that. See, that's what happens. It says less than or equal to. I got to do it one more time. So that's going to happen a total of n plus 1 times. Then we're going to do one more comparison, and we're going to be done. So that's 3n plus 1 plus 1 more, 3n plus 4. That's big O of n again. Now, why did we do a worst case analysis? Why did we say the worst thing that could happen is the thing I want is either there or not there at all? If we know the largest number of operations, then any other data set will be an improvement on this. And that's the important part. We need to get no worse than. Because remember, big O is an upper bound. Everything else will be smaller than this. Normally, I'd say questions. You're not here to ask them. So think, pause the video if you need to. Think about this. I'm going to give you a brand new problem, an algorithm we've not seen yet. Now, this, by the way, is the same sort of programming algorithm task that a lot of Google interviews use and a lot of coding companies say, hey, tell me about this. So here's an algorithm. The procedure takes a list I need to write this as a piece of pseudocode. What they've given me is just a loop. M equals 0 for I equals 1 to n, for j equals I plus 1 to n. M equals max aij comma m. Oh, okay. This is part of an algorithm. So my question is, how many times does this run? We have a multiplication and a comparison. So this line does two operations. How many times does that line get done? Oh, the problem is it's inside two different loops. So we need to figure out how we're going to count these. Hey, wait a minute. This is just like our double sum in our sigma, in our summations. So let's try and write it out in that notation. So I'm going to think about what happens when I equals 1. Then j is 2, 3, 4, n minus 1, n. Because it starts 1 bigger than I. And then we do that whole set. Oh, wait a minute. That's n minus 1 times. And so then we increment I. What's j here? Oh, j starts at 3 this time. That's n minus 2 times. I equals 3 means j starts at 4. N minus 3 times. Eventually, I'm going to get to the end, right? I's got to get all the way up to n. J starts at 1 bigger. 1 bigger than n minus 2 is n minus 1. That's only 2 times. Here, j is n, means that does 1 time. Here, wait a minute. That's no times at all. There is no n plus 1 in the list. J starts at biggest at n. Oh, so how many times does this thing get done? The two operations get done that many times. Wait a minute. I'm going to write those in the other order. 1 plus 2 plus n minus 2 plus n minus 1. That's the sum of a bunch of numbers in a row. We came up with a formula for that. Remember, they come in pairs, right? Those two add up to n. Those two add up to n. So it'll be n for a total, and it'll happen that many times. If I multiply those together, wait, there's a 2 on the outside. The 2 cancels the 2. That means that this is big O of n squared. Even with having never seen this procedure before, I know its complexity based on my ability to count steps. I like that. Now, a lot of what we do when we measure complexity is based on our general analysis. We're going to try and do a worst case. Today's lecture, guest lecture, should be talking about the binary search algorithm. If you look carefully at our binary search algorithm, and hopefully our lecturer today discussed this, but if not, it's example 3. It turns out that when we do the binary search algorithm, we're really only counting the number of comparisons and the computation of m. Well, it turns out that's actually big O of log base 2 of n. Wait a second. The linear search was big O of n. The binary search is big O of log 2n. Which one is faster? The binary search is substantially faster. Oh, it turns out that that is a much more general statement I can make. The binary search is order of complexity faster than the linear search. Now, I prefer to do worst case analysis. In this case, the binary search worst case would tell me that the number I'm looking for is not in the list. And I would repeatedly cut it in half and cut it in half until I got to, oh, there's only one thing on my list. I equals J, spit that out. That's not the number I want. Return location is 0. Well, that's big O of log n because I kept cutting it in half. And if I had 32 things in half, in half, in half, in half, in half, one more to close out the loop, that's log base 2 of n plus 1. That's perfect. Depending on the way you desire to write an algorithm, are you willing to have lots of space and minimize your time, or are you going to play a trade-off of saving some space and costing you some time? So we have to analyze these things carefully. We did sorting. The bubble sort and the insertion sort are both big O of n squared. However, there are other algorithms that can make faster sorts. Things like the heap sort or the merge sort or the quick sort. Those are big O of n log n, which are faster. But these are recursive, and we haven't discussed recursion yet. We will discuss recursion in chapter 5. I'm just not there yet. For those of you who like matrices, I remember, Emily, I think it was you who asked me about matrices because we jumped over the section in chapter 2 about matrices. Uh, Matrix multiplication appears on page 235. We'll talk about matrix multiplication more in linear, which is our next CS course requirement. There's a lot of stuff that deal with weighted inner products and fastest algorithms for traversals of data structures. Those are almost always matrix-driven algorithms. But the way we design our algorithm matters. We talked about the change-making algorithm, and the change-making algorithm is a greedy algorithm. I seem to recall liking that to the stupid shipping maneuvers from Amazon. You always take the box that your stuff fits in that's in front of you. You don't go search for a better box. You send it with the box you've got that's biggest, that fits your item. Sorry, that's smallest that fits your item. And that's how you end up getting a SIM card in a box a foot square. But Cashier's algorithm and greedy algorithms in general is a way of thinking. I'm going to give up going and finding the better fit to get the next step immediately. In graph theory, we talk about Prim's algorithm and Kruskal's algorithm. For minimum spanning trees. Minimum spanning trees are network backbones. They're the minimum necessary number of connections to keep a network up and running. So again, it may or may not be something you're going to do. Knowing what a minimum spanning tree is allows you for fastest network pen testing. How do I get through to all of these computers as quick as possible? There's another algorithmic paradigm, and it's based on a different design, and that's brute force. Now, brute force is a very easy code. It trades simplicity of code for time. These are usually inefficient. But they're usually fairly straightforward in terms of coding. I'm going to give you one. It's my favorite brute force algorithm. It's called the shortest distance algorithm. I'm going to give you two collections of points or two sets of data. So here's our data set: x1, y1, x2, y2, xn, yn. A set of points. Tell me which two are closest together. Well, remember the formula for distance the distance between xj, yj and xi, yi, sorry, didn't mean to write the square root yet, is the square root of change in x squared plus change in y squared. But the problem is, in order to do this, I need to check all the distances. So what I need to do, and this is going to look familiar, is I need to do the following. Start by setting d equal to 0. Then take the first point and compare it to all the rest of them. Now, the reason I said that this algorithm should look familiar is that except for the calculation part, that's the same as this. Here we did take the maximum of this calculation versus that. Oh, so here I've got 1, 2, 3, 4, 5 operations and a comparison. This is 6 operations in this line. And I do it how many times? Oh, so this is big O of n squared. In spite of the fact that this is no more complicated than a sort. It's really a very inefficient algorithm because you're going to compare every single pair of points, no matter how distant or close they might be. If you could tell me by looking at your points, it is fairly unlikely that the smallest distance will involve this point or this point because there are points that are clearly closer together, right? But that's a human note and a global examination rather than a local examination. For all I know, it could be that there is another couple of points right there and right there, that maybe those do require things to be looked at more carefully. Part of my PhD thesis was related to this. There's something called the Hausdorff distance, and that turns out to be related to fractals. And I want to keep talking about this. Normally, if this were Monday, I'd say we're going to do this on Wednesday. But Wednesday is Founders Day. So we're going to pick up this discussion on Friday and finish out our discussion of algorithmic complexity. And that includes one of the $1 million questions being asked. So if you've got the chance between now and Friday, you should look at the Clay Math Institute's Millennium Prizes, and we'll talk about computational complexity more on Friday the 21st. I hope you gave your attention to the guest lecturer on today the 17th. I will see you later.